In this video, we're going to take a look at Newton's method. So let's try to find a solution to the following equation. Let's say we have 2 root x plus 5 times x to the 4th is equal to 100. So we'd like to find a solution to this equation here in the interval from 1 to 3. And let's say that in this problem we'd like to give our final answer to 2 decimal places. So there is a typical Newton's method problem. Now just a note about the notation here. This interval here could be re-expressed as the x values that are greater than or equal to 1 and less than or equal to 3. So we should be familiar with the two types of notation here. So we're just trying to find an x value in this interval that is approximately a solution to this equation. We want to give our answer to 2 decimal places. So the tip-off that it's a Newton's method problem is that the problem is asking us to find a solution to a particular equation. So that's what tells us right off the bat, Newton's method. So to get going with our problem then, we'll need to decide what x value we would like to start with. We'll do that in a minute. And then once we have our starting x value, we can build ourselves a little chart to figure out our next x values. And to do that, we're going to use the Newton's method equation, which we developed in class. So our equation says that our next x value is just our current x value minus the value of our function divided by the value of its derivative. So I'm going to put that in a box. This is the main equation that we'll be using as we go through this problem. Now, one thing that we have to be careful of is this f of x that comes up in the formula. When we're doing Newton's method, f of x must always be equal to 0. So whenever we're doing Newton's method, we may need to do a little bit of rearranging here to make that happen. So if you look back at our original equation here, we had this expression involving x was equal to 100. Well, first thing we're going to have to do is just move everything over to the left so that our equation looks like 2 root x plus 5x to the 4th minus 100 equals 0. So it's just as simple as moving everything over to the left before you start talking about f of x. So this whole expression here, that is our f of x that we're going to be working with in this problem. This step is very important. If you forget to rewrite f of x this way, the work that we're going to put into our calculation will not lead us to the correct answer. So we've got to have f of x written this way in order to get on the right track. So with that, now we can talk about our starting x value. The clue that we were given in the problem is that our solution x is going to lie between 1 and 3. So what I would normally do is just make a little chart here. You can write down some x values and some f of x values, and we'll try to choose a good starting point here. So normally I would just test the integers that lie in our interval. So we could check x values 1, 2, and 3. And what we're looking for is a place where f of x gets pretty close to 0. Remember, that's what we're trying to do in this problem, is figure out where is f of x equal to 0. So let's plug these 3 values into our function, into f of x, and we'll see which x value leads us to a value that's closest to 0. All right, well, if we plug x equal 1 into our function here, we get negative 93. If we plug x equal 2 into our function, into f of x, we get something that is approximately -17. And plugging in x equal 3, we get something that's approximately 308. So these are our three values here. We're looking for the f of x value that is closest to 0. That certainly comes in this middle row here. So what we want to do is choose the x value that works the best. The best x value that we're looking at here is 2. So that's how we decide x0 equals 2. Now we can get into our real Newton's method calculation. It's nice to have our formula for f of x sitting right in front of us when we do this. So let's calculate f of x and let's write down f prime of x as well to get us set up for our calculation. So as we said before, f of x is 2 root x. I'm going to write that as 2x to the 1/2 plus 5x to the 4th minus 100. Okay, so we're just copying that from over here where we did that previous calculation. Now f prime of x, we'll take our derivative. We're going to have 1 times x to the minus 1/2 plus 20x cubed. Okay, so that way we've got f of x and f prime of x all organized for us. Now here comes the key part of the calculation. I like to build a chart for Newton's method. It allows us to show our work, and it allows us to also double check our work fairly quickly. So what we're going to do is have a little column that represents our x values. And at each step, we're going to calculate the value of our function. So let's call this f of xn. We'll calculate f prime of xn. And then once we've got all these values here, we can actually figure out what our next x value is going to be. And that comes from our Newton's method formula. x0 is equal to 2. We're going to take our x value and we're going to plug it into our function. Now, if we try that, we're going to find not such a nice looking number. It's going to have a long decimal expansion. So let's just remember that we're trying to give our final answer to 2 decimal places. That was given in the question. And so we want to do our work to 2 extra decimal places. So number of decimal places here. We were asked for 2 decimal places in the question, and we're just always going to add 2 decimal places for accuracy. So if you were asked for, let's say, 3 decimal places in the question, do your work to 2 extra decimal places. So in that case, it would be 5. In this case, 4 decimal places will be enough to give us the accuracy that we need. So plugging x0 equal 2 into our function, we get about -17.1716. Okay, so it might be a good idea to pause the video here, maybe work out some of these values, and then just use the video to check your answer. This part of the calculation, the part of building the chart, is the part that students often underestimate. Often they think, oh yeah, pretty straightforward to plug into the calculator. But you might be surprised that sometimes you need to do these calculations twice, or at least double check them to make sure that you're really getting the correct answer. So plugging x0 equal 2 into our derivative, we get 160.7071. So again, that's rounding off to 4 decimal places. And then in our last column here, we're just going to take our x value minus our function divided by our derivative. And just be careful here because we do have a double negative going on in this step. So to 4 decimal places, we should get 2.1069. All right, so that is our first step completed. We're now going to take this x value and we're going to use it as our x value for the next step. So x1 is 2.1069, and we'll repeat the process with this next x value here. Plugging x1 into our function, we get 1.4279. And again, I would encourage you to pause the video, calculate some of these values, and really just use the video to check your work as we go through this. Plugging x1 into the derivative, we get 187.7407. And then for the last column in this line here, we're going to do the x value minus the function divided by the derivative. So that gives us 2.0993. Now at this point, we're probably starting to ask ourselves, how do we know that we're done? So the secret is that we need to give our answer to 2 decimal places. So after the first step, we found an answer of about 2.11 if we round that off to 2 decimal places. So I'm just going to write that in brackets beside here. If we stopped after one step, our answer would be 2.11. If we stopped after the second step, our answer would be 2.10. Now we have a bit of an issue here because these two values do not agree. So we're going to continue until we get the same x value coming up twice in a row. So if we repeat this process one more time, if we get something that rounds to 2.10 in this next step, we'll be able to stop. If it rounds to something different, we'll have to continue until we have that agreement. Okay, so next step here. x2 is going to be equal to 2.0993. And let's run through these numbers. When we plug x2 into our function, we get 0.0087. When we plug x2 into our derivative, we get 185.7250. And then when we do this calculation here, x2 minus the value of the function divided by the derivative, we get 2.0993. Okay, and if we were to stop the problem after this step, we would have an x value that rounds to 2.10. So happily now, we're done. Okay, so we stop when we have agreement at 2 steps in a row. The fact that these two x values here agreed to 4 decimal places, that's just sort of a happy coincidence. What we're looking for is agreement to 2 decimal places, because that was the original precision asked for in the question. Okay, and that's how we know we're done. So x approximately 2.10. That is our final answer to the problem. Oh, just highlight that there. X approximately 2.10, final answer to the problem. If you wanted to check that, you could go back to your original equation here, try plugging in 2.10, and just make sure that it roughly solves the problem. Won't be an exact solution in most cases because remember, we're approximating the value here to 2 decimal places.